Hi, I'm Sala. In this video, we are going to estimate the unknown force to a, say, second order system, say mass spring damper, and we are going to do it in three ways, with H2 and H infinity observers, let's say, and myosynthesis. Actually, this case study will comprise several videos, and in this first one, we will concentrate on the problem statement and the uncertain system modeling. The basic idea is that we will have a system which nominally has this transfer function, the second order one, multiplied by the sum of two inputs, a known manipulated one, U, and an unknown force, F. So we wish to craft an estimator of F given measurements of P and those of U, because as it is a manipulated variable, we'll assume it to be known and available for our observer. Our model will incorporate a couple of refinements. The first one is that we will assume the force to be band limited, in the sense that its spectral content at high frequencies will be assumed to be smaller than that at low frequencies. In particular, we'll assume that the force is the output of this filter when subject to an input with a unit power spectral density, in the case of H2 optimization, or to a worst case amplitude of 1 at every frequency. So this will be either a colored noise in Kalman minimum variance stuff, or a worst case amplitude that decreases with frequency from 0.4 radians second onwards. So we'll get this pole, which will be the pole of this filter in our model. Our second refinement will be considering the coefficient that multiplies S, sort of friction damping, to be partially unknown. If this were a mechanical system, friction force will be some coefficient B times the speed, so acceleration will be such force divided by mass. But well, we'll assume B to be uncertain, so the acceleration due to friction will be uncertain, and it will nominally be -1, but it will have some interval of uncertainty, and such interval in particular will have a half width of 0.55. So our friction may range between 0.45 and 1.55 times the velocity, and we must incorporate that into the model. Having this uncertainty is what will make us use myosynthesis as the right way to solve the problem in a particular setting. However, for robust control, this uncertainty must be expressed in linear fractional transformation form. So we'll model our system with this block diagram. In particular, we will have this delta that I call delta 1 because it will be a normalized uncertainty taking ranges between plus and -1, and I multiply that by 0.55 to account for the actual width of the damping interval. So I will have two cascade integrators that from acceleration will give me velocity and position. This -5 will be sort of equivalent to a spring in a mechanical system, -5 times the position, that will add up to the force balance, so to the net acceleration, and I will also have it as an output of this stuff in order to use it in my observer sensor, of course contaminated with some measurement noise not present in this diagram. Then this -1 will be the nominal acceleration due to friction. So -1 times speed is also added to this net acceleration sum block. But also we will add the speed multiplied by something between plus -1 multiplied by 0.55. So this arrow here will account for the uncertainty in the friction coefficient, And last, we will add 2 times the known input and 2 times this disturbance force in this acceleration balance, so we will have the block diagram form of the system we wish to deal with. The last ingredient will be inputting this sort of normalized disturbance with power spectral density 1 or worst case amplitude of 1, depending on my H2 or H infinity problem statement. And it will go through this low pass filter, giving me the actual force that, multiplied by the same thing as my U, gets into the balance to output the net acceleration. And that actual force will be an output of my system, not because I can measure it, but because I will need it to compare to the force estimate given by my observer to check such observer's accuracy. As it is the output of this first order system, it will be state of the overall third order system, which is surrounded in yellow. So this is why we are calling our developments in this case study as an observer. But it's an observer with an uncertain model. So it will have some nuances compared to, say, the usual Kalman or pole assignment stuff. So good. We'll need to input this into MATLAB's toolbox, and we could use the connect stuff to programmatically generate block diagrams. But anyway, we will use state space representation and then LFT interconnection of the uncertainty, because the block diagram can be expressed as these differential equations. The derivative of the position is the velocity, and the derivative of the velocity, the acceleration, will be minus 5 times position, minus 1 times velocity nominally, plus 2u plus f, the input forces, known and unknown, plus 0.55 times z, the output of this uncertainty block. This is 0.55 z. Apart from that, we have the force as the state variable and output, in this case, of this low pass filter, which has this highlighted equation. And the only remaining equation is saying that z is some normalized delta times the velocity. Here we have it. Well, v is expressed as vel in the equation's velocity, because later on I will use lowercase v as measurement noise, so kind of be aware of this change in notation to avoid confusions in a later stage. So these first 3 equations will be the state space representation, the state equations of the known part of my system, which will be connected in LFT to the unknown part of my system. So we will code it in MATLAB, saying that delta is an uncertain real number with nominal value 0, and if we say nothing else, its variability is already scaled to -1 plus 1. And then, if states are position, velocity, and capital F, then this says that the derivative of position is velocity. This -5, -1, 2 correspond to this -5 position, -1 velocity, and 2 times F, which is the third state. And then we'll have also 2 in the B matrix, multiplying a known input, and 0.55 in the B matrix too, multiplying this stuff that will actually be unknown and uncertain. So the B matrix has nothing in the first equation because derivative of position is velocity period, nothing else, but in the acceleration balance I will have 0.55 times the first input, this z coming from the uncertainty, 2 times the manipulated input u, And third input will not appear in the acceleration balance. It will only be an input to the low-pass filter, the third state. So I will have this 0 here, and then indeed the third state equation, this one tells me that the third state's derivative depends only on itself with this pole, and this 0.4 is also multiplying the third input in the B matrix. Here it is, but this W stuff doesn't appear anywhere else. So this is the A and B, the important stuff. And then which are the outputs we wish to output? Well, first the speed, that will be multiplied by uncertainty delta, the force to be later compared with the observer estimation, and the position to be measured. So we define these three outputs. Velocity is the second state, force is the third state, and position is the first state. So once I have the known part of my system, the uncertain system for robust control toolbox will be the LFT interconnection of this uncertainty delta normalized and this GS1 linear time invariant system, which is encircled in this yellow boundary in this block diagram. So this GS-nth has this step response, no uncertainty regarding the force, in the sense that when I have a step in manipulated input, capital F doesn't move, and with a step in this normalized disturbance, then I get this low-pass filtered first order step response. But then regarding the position of this mass spring damper, as I have uncertainty in the damping, then I have uncertainty in settling time and overshoot, for instance, which is seen in the subplots at the bottom row. So we'll finish with this. In this video, we have modeled this nominal plant with an unknown input and uncertain damping. Okay, so we have modeled this as this block diagram, including a band limited force, and then this block diagram is divided into a known part, the bottom LTI subsystem, and an uncertainty part. So we wrote the equations from that block diagram, and uncertainty was this delta. The linear time invariant was input with the highlighted lines, and this LFT made the whole interconnection so that robust control toolbox was able to output an uncertain step response. So we finished here the modeling phase, and then what remains is crafting a suitable generalized plant and call the H to H infinity or musin code, but that will be, for brevity, discussed in a second video continuation of this one. For the moment being, we end here. Thanks for watching.